All right, let's get right into it. Today we're tackling a massive challenge, one that pretty much runs modern science and engineering. How in the world do you solve not just one or two, but maybe even millions of equations, all at the exact same time?
So let me start with a question for you. What do your phone's GPS, the weather forecast you checked this morning, and a giant skyscraper all have in common? They seem totally different, right? But they actually share a secret ingredient.
And that secret ingredient is this. They all rely on solving huge, and I mean huge, systems of equations. It's the invisible mathematical framework that lets us build and predict things in our incredibly complex world.
So let's peel back the layers on this. What exactly is this universal puzzle? Because it turns out it pops up almost everywhere.
At its very heart, it's a simple idea. You have a bunch of equations that are all linked together. The goal, the big puzzle, is to find that one magic set of values for x1, x2, x3, and so on that satisfies every single one of those equations simultaneously. If we're just talking about two equations, it's pretty easy to picture. You can draw them as two lines on a graph. And the solution? It's just that one single point on the graph where the two lines cross. Easy enough. But what happens if we throw in a third equation? Well, now we're not talking about lines anymore. We're talking about three flat planes in 3D space. And we have to find the one point where all three planes meet. Okay, but what about four equations? Or 1,000? Or 1,000,000? Forget it. Our brains can't even visualize that. We need a much, much more powerful way to handle this. And that brings us to the tool that lets us do it. Matrices. Think of this as the special language, the decoder ring, that was invented specifically to crack these incredibly complex puzzles. So what is a matrix? You can just think of it as a super organized grid of numbers. It's a way to take all the messy numbers from our equations and put them into a neat, tidy box with perfect rows and columns. It's the ultimate organization system for this kind of chaos. And here's where the magic happens. On the left, you see the jumbled mess of equations we start with, but on the right, look how clean that is. It's been translated into this elegant form. A times x equals b. That A matrix is our grid of coefficients, x is a list of our unknown variables, and b is a list of the outcomes. It turns chaos into order. Okay. So we have the code. How do we actually solve the puzzle? Well, we play a game. A very systematic game called the elimination game. The most famous version of this is called Gaussian elimination. It's really a two-part game. The first part is called forward elimination. The whole point here is to cleverly subtract one equation from another to create a whole bunch of zeros. The goal is to get this clean staircase of zeros in your matrix. Once you've done that, you move to part two, back substitution. Because now the last equation is super simple. You solve for that last variable, then you plug that answer into the equation above it, and you just work your way back up the staircase. Let's make this feel real. Imagine you're tracking a rocket. You have a few data points, its velocity at specific times. You want to figure out the smooth curve, the polynomial that describes its flight. Well, guess what? That problem turns into a system of three linear equations that we need to solve. So we take our rocket data, we put it into that starting matrix, and then we play the elimination game. And this is what we're aiming for, this beautiful, clean, upper triangular form. See that neat little triangle of zeros in the bottom left? That is the whole point of forward elimination. It means we've turned a complicated, tangled problem into a simple, step-by-step puzzle. And after we do our back substitution, working our way up that staircase, we get the exact coefficients for our velocity equation. Now we can predict the rocket's velocity at any time we want. So at 6 seconds, for example, the velocity is 129.686 meters per second. A precise, real-world answer. All thanks to this process. But there's a reason the method I just described is called naive Gauss elimination. It has that name because it works great until it doesn't. There are a couple of dragons hiding in this game that can make the whole thing just break. Pitfall number one is a showstopper, division by zero. The process relies on a key number on the diagonal called the pivot element. If that number happens to be zero, the math falls apart. Game over. The second pitfall is way sneakier: round-off errors. Computers can't be perfect. They round off numbers at some decimal point. And when you're doing thousands or millions of calculations, these tiny, insignificant rounding errors can add up and snowball until your final answer is wildly, completely wrong.
This problem is especially bad for something called ill-conditioned systems. Here's the best way to think about it. Imagine trying to find the exact point where two lines cross, but the lines are almost perfectly parallel. A tiny, tiny little nudge to one of those lines, and the intersection point goes flying miles away. That's an ill-conditioned system. It's super sensitive to those tiny little round-off errors.
But don't worry, for every problem, engineers have come up with clever solutions. These are the smarter, better, and faster techniques that let us actually use this stuff in the real world without everything blowing up. The biggest and most important fix is a brilliant trick called partial pivoting. It's a simple upgrade to our elimination game. At each step, before it does anything, the computer quickly looks down the current column and finds the number with the biggest value. Then it just swaps that entire row up to the top to use as the pivot row. This one, simple move, magically avoids dividing by 0. And it drastically reduces the damage from those pesky round-off errors. It's a total game changer.
And pivoting is really just the beginning. The modern toolkit for this stuff is amazing. You've got methods like Gauss-Jordan, which is a variation that's a bit slower but spits out the answer directly. You have LU decomposition, which is incredibly fast if you have to solve the same puzzle with different final numbers over and over again. And for the really enormous systems, you've got iterative methods like Gauss-Seidel, which basically makes a smart guess and then refines its own answer over and over until it lands on the perfect solution.
When you step back and look at it, these tools, from a simple elimination game to these advanced methods, are more than just math. They are the keys that unlock our ability to model and predict the world around us. And that leaves you with one final big question. What other incredibly complex systems in science, in medicine, in economics are just sitting there, waiting for us to find the right equations and the right key to solve them?